All right, continuing on with the energy methods of week 2, we have another additional example that is not in Dr. Bob's notes, and I don't know. Am I adding too much to the thing? Is it worth it? Is there value added here? Well, it's hard to say. I don't know the answer to anything really anymore, but I don't feel bad about it. All right, so we have previously found the natural frequency of a pendulum using Newton's second law. Let's go ahead and use energy method. One aspect to start with here, I'll just pick this at random, that H can be found if we happen to know the length and the angle right there, right? So that's the difference, the change in height, as we were putting it right there. I'm going to use this side over here. So we have, I'm going to use the rotational type of kinetic energy, T-rot, trot. And I don't know why, I wrote down an I, we've been using J, I jumped back to I. Here's what we're used to seeing this before, but of course this omega is theta dot. For a simple thing where it just has a mass down at the end, you can find that by taking the mass and multiplying it by the length squared. Right? So hopefully you believe that that is the mass moment of inertia of the thing. And here we go back to the theta dots. I don't know why I went back to the omegas and the i's. I just did. And I didn't even need to write rot. That's the only omega that's there. We could also go to here. It's going to be the potential energy is mgh, which I just established that height is going to be L times 1 minus cosine of theta. All right. It's the same thing that I just pulled the L out. So let's say that we have that equation T plus U equals 0, and then take the time derivative of it. I'm sorry, T plus U is equal to a constant, but if you take the derivative of it, it's got to be equal to 0 because the derivative of a constant is 0, right? So you go ahead, let's go ahead and write that over here, dt, and put that in as 1/2 ml squared theta dot squared plus mgl 1 minus cosine theta equals 0. Okay, so we can take the derivative of that with and we end up, okay, so the 2 cancel, so we're going to get ml squared, then we get a theta dot, and then we get a theta double dot, plus mgl sine of theta, but we also need to take the derivative, theta dot, and multiply by it, equals 0. That theta dot goes away, and m goes away, and oh wait, one of the l's goes away, and that squared goes away, right? So we end up with theta double dot plus g over L times the sine of theta. It's not very good, L. This sounds a little better. Equals 0, but we remember that that was a difficult integral, so use the small angle approximation, approx. And what we end up with is theta double dot plus g over L theta equals 0, which is the equation of motion that we had before. So this is the energy method to get the same thing. It's not a drastic change from the other, but it's just another example where we're able to use a different method to get the same thing. So it only took 5 minutes to do that. I think that's the last. This one coming up is the last example, but I think it will take a little while. It will take a little while. So let's make another video. See you soon.